This talk is from the LinuxCon in China. I adapted it to, to do that in, less time, because the talk was composed of two parts. The first was, a discussion with people from Red Hat and Google and Baidu, on networking in containers, and then there was the talk. So it was composed of more topics. CNI is a project that, as a few others, joined the CNCF. It was born as an independent project on the organization Container Networking on GitHub. The purpose of this project is to standardize the way we put networks inside containers. I haven't chosen the put verb because I didn't know the real word, but because CNI actually puts the network inside. I mean that the network namespace is when the network namespace borns, it has no networks, and after that the network is actually hard-coded in that after a few seconds. The CNI project is used in a few projects, which are Kubernetes, CoreOS, OpenShift, Apache Mesos, and the others. Actually, it is not used in Docker by default. In Docker, you have libnetwork, which uses the CNM, which is a container network model. The two projects are quite similar, I think, but CNI is a project designed to be extensible, while libnetwork is a project that implements its own specification. That means that libnetwork is CNI uses external plugins to provide networks to your containers, and libnetwork could be seen as at the same level as a CNI plugin. So I did some speculation on that on Twitter, because you could actually use libnetwork as a CNI plugin if you write a wrapper, right? So that could be interesting to see that there was a huge flame on, oh, why did you do CNI? We have libnetwork and all the things. Why libnetwork can be used as a plugin in CNI, So if you were thinking about the differences between the two, they are not the same thing at all. They are aimed to provide network to containers, but in the end, CNI doesn't provide network to containers. It's just an adapter layer to network provider to containers. So libnetwork could be one. In these terms, CNI is just, if you look at it, you enter in the repository like I did before. If you look at the project, it's not that complicated. I mean, it has it's a more comical than technical presentation. So the actual thing, it's happening in where? PKG. In PKG and in libCNI, there are, a few things. Where? Yeah, it's better that I go to the on Git. Okay. At least it's a browser. So this is the library used by the clients. CNI 2, okay. So the thing is very simple in terms of how it's implemented. CNI is just CLI program that calls a binary you provided to it. So the container runtime, for example, Kubernetes, which uses Docker, and Kubernetes calls CNI to put the networks inside Docker containers or inside, CRI-O containers or ANSI containers in other implementations. What happens is that there's that libcni that you saw, which is used in the container runtime. We will have diagrams on that, which is used by the container runtime to configure the plugin that you use. So in simple terms, CNI just is just called by the container runtime and calls the plugin you configure. So it's just, a pass-through. In other terms, the two main terms of the glossary of CNI are container and network. These terms are pretty similar to what happens in Docker libnetwork CNM model, in the way that for CNI there's a container, which is, a container is not a first-class citizen or something like that. It's just, in Linux, at least. I don't know if in Windows it is, but I don't know Windows. So, container word was born to, group a few things like the kernel namespaces, the C groups, seccomp, armor, and all the things that you actually use to isolate that process from the rest of the machine. So that's the container part. In terms of CNI just consider the Linux kernel namespace part. And there's the network definition, which is basically the group of entities that can be addressed by CNI to configure the network inside the container. So all the devices, the network cards, which are not even virtual, but are just defined in that specific namespace. Plugins are responsible for EPAM, IP address management. It's not that you don't need the DHCP in containers, but that will be, if you have an orchestrator that it's aware of every container, why would you need the DHCP? The ACP, in Italian, DHCP, so, okay. The ACP is, it's more useful when you have machines that just spawn up and announce themselves in a network. So it's not the case for containers. Containers are actually orchestrated by who manages them. So IP address management is lightweighter and more, easier to maintain as type of process for IP address management. They are responsible to connect VIF pair. I actually learned the pronunciation of VIF at DockerCon. I previously called them VIET, so in Italian probably. VIF pairs are basically, you have two computers with two network cards, and you put the cable in the first and the other part of the cable in the second. That's a VIF pair. So whenever when you have a container, that container is an isolated namespace. In that container, there's a network card, which that was not born in that container. That was born in another place on the on the host. Thank you. And that network card is then unshared in the container, and the network card is can be considered as the same thing of the network card living in the host. So that's the pair. There's a network card in the host, there's a network card in the container, and them are just the same network card. Being the same network card means that every single byte of traffic that arrives to one card arrives to the other, so every single byte of traffic that arrives in your containers can be listened, obviously, in the host. And that's why bridges exist, because if you want to connect multiple VIF pairs, like connecting multiple containers in the same network, you need a bridge to, because a VIF pair is just a cable between two cards. If you want a cable between three endpoints, three taps in technical, the technical term is tap for the pair, you need something to aggregate the communication. That's a bridge, or you could, just break the cable and put things together. That doesn't work. And it adds necessary network components like bridges and all the things. So this is basically what I said. There's a container runtime, which in my demo was me, because I was orchestrating CNI. So what I said, that the container runtime, which in Kubernetes, for example, can be seen as Kubernetes and Docker, or Kubernetes and CRI-O or runc, or that could be another container runtime. That could be you that just call the CNI. That could be, in my demo, is me that creates a namespace, and then I call the CNI binary to put the networks inside the container. So that CNI tool that I showed you before, which is the CLI tool, is just there so that you can actually use that tool to do the unsharing of the network, to do put the networks in the containers. But usually in runtime implementation are using the libcni, not the CLI tool. So there are a few built-in plugins which are basically the basic implementation of networks. There's IPvlan, MacVlan, Bridge, PTP, that's point-to-point, Flannel. Flannel is actually built-in. And there are third-party plugins like Cilium, OpenVSwitch, or Calico. There are a few others. I hadn't enough space. So this is, how they are configured. It's very simple. You put in a directory, which is etc CNI and something. I don't remember. I had that in the script. You put that configuration. This configuration says create a network called mynet and use, what? Yeah, and use the PTP point-to-point plugin. So mynet, it's matching with the name of the actual network namespace I created. So in the demo that Gianluca will do. There's basically EP, netns, add mynet, so that's just a network namespace. It's configured to use an EPAM, root to host local, which has this address, this seed address, and the name servers for that are those name servers. So very simple. This configuration creates a situation like that, where there are the two namespaces, the NS0 and S1. Those are the network namespace in the host and the network namespace in the container, and that's a simple point-to-point connection. So there's a VF pair in the container and the heads in the the VF pair in the host and the heads in the container, and the container can connect to the host but can't connect to other containers. I often do wrong things in the simplest implementation. Then there's the bridge plugin. This is commonly used to connect container on the same host. When you have also a multiple host setup, you are actually always using the bridge plugin, because also if you are multiple hosts, you don't want to involve the multiple host thing, which we see in the next slides. when the container you're actually trying to connect is in the same host. The name of the network namespace is I'm the best net ever, which is the NS one. Then there's, the driver is bridge. As you can see, there are a few, those are written in the specification, default configuration routes. And after all the, like EPAM type and name, and there are all other fields that are specific for that plugin. You can define those in your custom plugin, or you have to actually look at the code documentation of that specific plugin to have them work. In this case, there's that situation I described before. So there's a bridge that actually helps you to, connect multiple containers. I could easily add another namespace in that situation with the BR tab on the bridge. And those three namespaces can connect to each other easily. So that's just that. That's the basic situation. You have, this is your server, just the network part. You have a loopback interface and hopefully another network card if not what you do with the server. The server is just connecting to the internet and receiving, or to the, your network inside your company and receiving things. And it's very boring because there are no hidden namespace in nothing. So there's no troubleshooting involved. And when we created that mynetNS, what happened? The container runtime actually asked for a namespace. It created it. The container runtime creates a namespace. In the actual Kubernetes implementation, what happens is that you ask for a pod. The pod asks Docker for a container with a network namespace and all the things. The network namespace is created empty using, in Docker it's called the null driver, okay, which creates just the network namespace with the loopback interface. And in other implementation like, Cryo, the thing is that way by default, so it's easier. After that, the container network interface, after doing that, its work, called the CNI plugin. The CNI plugin does a few things that are create a network interface, a pair in the container, which is this one, ATH0 with its own IP address. It creates the actual bridge, CNI 0. This is the bridge implementation, which has its own IP class, and create the pair on the host. This is the network interface on the host, which, as you can see, this is like the output of EPA command. When you see, I can do that probably. At least I can do this, I think. It's the same thing as this. You have, Gianluca actually has a container, so I can puke in those. So it's not the CNI, but that's the same topic. So what?
Jekyll one, loving bar.
I'm using potato. I prefer. I think potato is good. So Docker. As you can see here, there's the ATH0 at if11 and 10 ATH0 if 11. And in those there was 11 we have something at if 10. So that's the actual VIF pair. and as you can see here, there's the IP address of the container. There's a process in the host, which is unsharing the namespace. So every namespace that you have in your where is the container? Anyone sees Docker or? Sorry. Where?
Scroll up. Yeah, there you go.
Yeah. ATCD. Okay. As you can see in this in this thing, there's the Docker daemon, right? That's the same also if you add the Kubernetes cluster, but different in the way that the things are not managed directly by the container shim. There's Docker D, which starts the Docker daemon. After that, that process called container D, which is the actual container runtime implementation. Container D uses shim to manage the namespaces. Okay, this is done in that way so that there's no single point of failure for the namespaces, because if that were managed by the container D itself, if a container crashes, it could crash other containers as well. So in that forest, what happened is that Docker, Docker in this case, because that's a Docker implementation, creates a container. It's empty. CNI with a network namespace, an empty network namespace, like if I was saying, the network namespace is created. It's empty in this case, and then the CNI creates a network card inside that, but it couldn't create that network card directly because inside the container there's no, there's no awareness of what's outside. So the network card is actually create the network card, something like that. It's actually create outside and then it's put in the container, injected in the container. Thank you. As you can see, Docker, and it's the same also when it's managed by Kubernetes, creates a network namespace in its own directory. So since I was not using Docker for this demo, it just does this thing, ipnetns create add, sorry. After that, you can see how the thing is implemented. So this is how things are done, basically. Everyone can see it. That's, actually quite simple. This plugin takes the network namespace of the container, which is this netns, and calls, passing on to that function the host network ns, so it can get some information, and it calls IP setup v8, which is a function that actually does the work, and add all the information to the actual implementation of the container runtime. This is the same thing that you saw in Docker. And this is, in Go it's actually very simple because there's this library which is used in basically it's used in every Go project I saw. So it's actually the implementation of how to call the syscall at kernel level to set up the interfaces is hidden behind that. So it's simpler, but it's not that simple if you look at how many syscall are needed actually too. So if you plan to implement that in C, probably you're not having your weekend. So I reply to your question, or?
Yeah.
Yeah. So that things happens, continuously. Even if you add another container, the plugin creates the pair interface, creates the interface on the host, but in this case the bridge is always there. So CNI, if you implement a CNI plugin, you have to implement it in an idempotent way because it's how it expects to work. If you implement it in a non-stateful way, what's the contrary of idempotent? Idempotent? In maniera non idempotente, in a non-idempotent way, you are going to have problems. At Kiratech, we are developing a few tools to, know better what happens in containers. At least we are developing a tool that's not yet open source, but it's a container comprehension tool. What I mean by container comprehension, when you use, 5 physical hosts, you have basically nothing to understand because the host is there. The network is on Ether. Yes, the light is visible, so everything's okay. In this room, I saw a few people fighting, mainly Leonardo over there, with physical servers. So you know what I'm speaking about. When you have virtual machines, things are getting difficultier. Things are getting even difficultier because on 5 hosts you create more and more virtual machines. You can imagine that with containers. When on a host you can possibly create an indefinite number of containers, depends on actually what is running inside those. So we thought that there's the need of container comprehension tools. In particular, this one, which we are redesigning because we actually are investing in that. It's a tool that, given a host, draws the actual interactions between containers and the host in terms of VIF pairs. But it's not just everything on a single host. It's also you might need to connect multiple hosts in different ways. You could possibly connect the host with virtual networks, which we'll see after, or you may have an already existent network infrastructure, maybe an enterprise network infrastructure that you want to keep because you don't have just container workloads, but maybe you have also VM workloads and physical machine workloads and whatever else workloads. Or you have a very battle-tested infrastructure you want to keep at the network level. So you might need to, go underlay. What I mean is that the containers take an IP address in the underlying, in the underlying gateway, in the underlying network infrastructure. So the IP address of the container is the same in the same class as the host that hosts it, or it's in the same network segment, the same network trunk of the rest of the company. So there are 2 ways to actually do that. The one way is IPvlan. I don't have to spend time explaining the JSON. What happens in there is that you have the network switch gateway, which is this one, and as you can see, the the host and the containers getting IP in the same class. It's not very, a good practice to give the same exact seed addresses, because in this world you have the ACP, and in this world you have the EPAM. So you have to understand how to assign IP addresses in an efficient way. But it's basically that. In this situation, containers are getting individual IPs on the network switch, but sharing the MAC address of the host. So it's called IPvlan for that. It's actually a thing implemented in the kernel. It's not that it's something implemented in CNI or in Docker or something like that. It's a kernel feature. Sorry. There's another thing called MACVlan, which is the same thing, but assigning a MAC address to each container. I think that's a better implementation in pure terms of maintainability, because by having a MAC address for each container, you can actually know what created the traffic. You can use a CMDB or something like that to map the network in your company. And also, that thing unfortunately requires you to put the host network interface in promiscuous mode, while the IPvlan doesn't require that. So if, for example, you are on a virtual, VMware or KVM or what you have, you actually have to put that host in promiscuous mode. That's not desirable in some terms, because another host can see the traffic on other hosts in this thing. But if you are on physical, you don't have this problem, because they're just container workloads probably. And then there's the overlay networking, which is very popular at the moment when talking about containers. It's very popular, but there's a little disclaimer that it's not really the best solution for every kind of workload. The VXLAN is not the best thing for every kind of workload. For example, I said that if you have an existing infrastructure, you can just put everything in a VXLAN. In that case, that's my car. Okay. In this case, what's happening, there are two hosts, which are those two colors. There are two containers, one on each host, and those are connected in the same network, in the same network trunk. As you can see, one has 0.5 IP and the other 0.6 IP. What happens there is that there's a tunnel called VXLAN tunnel. The VXLAN tunnel is also in this case something implemented in the kernel. The VXLAN is a kernel feature in Linux. What that does, when you add the network interface in the VXLAN, that network interface it's put in a shared bridge. On each host you have the bridge, and there's the need of something that orchestrates those bridge. In the Docker case, the Docker Swarm does that. In the Kubernetes case, that's done by Kubernetes with CNI, Flannel, or OpenVSwitch or Weaveworks. And those, it's part of the fact that why, for example, in Kubernetes, there's the need of etcd to maintain a distributed state, right? The distributed state, it's very useful for this kind of thing, because in this way, if you look, for your question, if you look at this network interface, you will see that it has this container. It has actually two cards. One is to talk with the inside containers, and one is to talk with containers on the distributed switch. You will see also that this container has a number, a TIFF something, that it's not even in the host, because it's in another network namespace, which is hidden from the user. I can show that after to everyone, which is hidden to the user. That network namespace contains the actual VXLAN interface, which is used to talk with the others. From a mere technical point of view, that is possible. On each host, we open the 4789 port, which is a new DP port, and Gianluca has made me laughing. And that's the tunnel port, and I mean, that's a UDP port. So how can I forward TCP traffic on that UDP port? What happens basically is that when this container asks, I have to do a TCP handshake with the other container. What I do? It calls with its own network interface. That network interface is a VIF pair with the other network interface. That network interface enters in the VXLAN, which is in another namespace, which goes to the distributed switch and says, I have this packet to forward. The packet is rewritten. It's encapsulated in a TCP packet. For this thing, when you look at this kind of interface, you will see a lower MTU. And the inner packet says it's for 6 and I am 5. This is the actual packet. And the other packet instead is a new DP frame with explain the real communication between the two hosts. By default, the VXLAN tunnels are not encrypted. You can encrypt them with IPsec. I was looking for a possible implementation with you weren't there listening to me? With DTLS, which is Datagram Transport Layer Security, which is the UDP version of TLS. And it's all that. There are a very astonishing number of implementation of VXLAN. The most useful one in terms of if you use Kubernetes, for example, by default you go with Flannel. It's not the best solution in terms of features. There's also OpenVSwitch and others. If you don't want to go with overlays, you can use SDN, but at layer 3 with Calico. There are also plugins that are not set up in networks, like Cilium, which set up an eBPF XPD set of filters, which are used, to provide firewalling, packet filtering to containers. This is the URL. The DTLS things I also said. This was my speculation on libnetwork, and thank you. And it's all.